Pilgrim 1 and Traveler 2 were excellent rockets, a long way from being customary models. They were fastidiously designed with sturdy structures and a pivot speed extensively slower than the hour hand of a clock. On numerous occasions, this design feature reduced apparent obscuring, permitting the spacecraft to capture both images and data simultaneously as they crossed the vastness of space. Even before their missions took them to the outer planets, their exceptional imaging technology had already begun to impress both scientists and the public. The spacecraft began transmitting pictures of Jupiter months ahead of completing their primary objectives. These early images, showing swirling clouds and the majestic Great Red Spot, captivated audiences at NASA's Jet Propulsion Laboratory. However, it was the discovery of active volcanoes on Jupiter's moon Io that truly stole the show. Slightly larger than Earth's moon, Io turned out to be the most volcanically active body in the entire solar system. The spacecraft's instruments detected continuous activity, which was confirmed by vivid images showing towering volcanic eruptions and a surface marked by volcanic deposits. One of Io's most remarkable volcanoes, Pele, erupted with a force many times stronger than Mount Everest, covering an area nearly the size of France. As the spacecraft's cameras shut down to conserve energy and memory before their journey into interstellar space, it is important to note that the photographs they captured did not include Mercury or Mars for multiple reasons. Regardless, NASA continued developing other remarkable spacecraft, including Pioneer 10, Pioneer 11, and New Horizons. On February 17, 1998, Voyager 1 surpassed Pioneer 10, marking the moment when Pioneer 10 was overtaken as the farthest spacecraft. Pioneer 1 continued its solitary journey for another 14 years, eventually entering the interstellar medium on August 25, 2012. Although there were no new major space missions on the horizon, NASA did not publicly announce this significant achievement until 2013. The S8 tension arose due to gravitational lensing studies, which suggested a lower-than-expected value for S8. Based on data from the Cosmic Microwave Background (CMB), research aimed at resolving the S8 anomaly has led scientists to examine various theories, from potential data errors to fundamental shifts in our understanding of gravity. Contemporary simulations, such as the Flamingo Project, have been instrumental in offering insights into the complex interplay between dark matter and gravitational forces in shaping the cosmic web. Despite the challenges posed by the S8 tension, many measurements at low redshifts and from the CMB remain consistent with the standard cosmological model. This has led to exciting speculation that the universe may have undergone significant changes, pushing us to reconsider our current theories about the large-scale structure and evolution of the cosmos. In short, the S8 tension represents a significant challenge to our understanding of cosmic structures and may necessitate updates to existing theoretical frameworks. Meanwhile, Pioneer 1 continues its incredible journey, reliably transmitting valuable data from the farthest reaches of the universe for nearly 50 years. Yet, in recent years, Pioneer 1 has begun sending back strange data, leaving the entire space agency stunned. Are these disturbing signals the result of a malfunction, or could they be messages from extraterrestrial sources? Join us as we investigate the truth behind these mysterious transmissions. For decades, scientists have been fascinated by the mysteries that lie beyond our planetary boundaries. This curiosity led to the extraordinary launch of Voyager 1 and Pioneer 2, among other prestigious space missions. These groundbreaking missions, celebrated for their achievements, began with the launch of Pioneer 2 from NASA's Kennedy Space Center on August 21, 1977. A few months later, on September 5, 1977, Voyager 1 was launched. These twin spacecraft, each weighing around 7,110 kilograms, roughly equivalent to a small car, were sent into space during a rare alignment of the outer planets, marking the beginning of their incredible journeys. The pioneers traveled at different speeds, culminating in a critical moment on December 15, 1977, when Pioneer 1 overtook its twin. Since then, Voyager 1 has become a crucial instrument, providing vast amounts of data and unraveling the secrets of space. Before diving into Voyager 1's latest astonishing discovery, which has shocked the entire space agency, we must first explore the spacecraft's incredible contributions, particularly its Jovian imaging mission in 1978. In 1978, Voyager 1 was positioned about 265 million kilometers from Earth. From this vantage point, it began transmitting thousands of images back to Earth. In January 1979, the probe embarked on a 100-hour mission, capturing time-lapse photographs of Jupiter's atmosphere. This treasure trove of 3,750 images allowed scientists to observe Jupiter's dynamic weather patterns in unprecedented detail. Shortly after, Pioneer 1 traveled through Jupiter's moon system and made a groundbreaking discovery: a faint ring around Jupiter, along with two new moons, Thebe and Métis. This expanded our knowledge of Jupiter's fascinating environment. To ensure a safe trajectory and avoid a potential collision with Titan, one of Saturn's moons, the spacecraft executed careful course corrections. Voyager 1 then continued its celestial journey towards Saturn, uncovering 4 additional moons: Mimas, Enceladus, Tethys, and Rhea. After completing its Saturn mission, researchers decided to conclude the planetary objectives of the Voyager mission and directed both Voyager 1 and Voyager 2 beyond the Sun's influence, speeding through space at an astonishing rate of 325 million miles per year. In January 1990, a new phase began: the Voyager interstellar mission. During this period, Voyager 1 captured some of the most iconic images in history, immortalizing the solar system and most of its planets. One key figure in extending the mission's goals beyond its original scope was the renowned astronomer Carl Sagan. As a member of the Voyager imaging team, Sagan passionately advocated for one final series of images as a farewell to humanity. Against all odds, his relentless efforts succeeded, and on February 14, 1990, Voyager 1, positioned 6 billion kilometers from Earth, captured the famous pale blue dot image. These breathtaking images, totaling 60, were added to the spacecraft's impressive collection of 670 photographs taken during its encounter with Neptune. Voyager 2, during its journey, made a remarkable achievement by recording wind speeds of over 1,000 meters per second, the highest ever observed in the solar system. As it ventured 298 kilometers into Neptune's methane atmosphere, it provided invaluable insights into this distant planet. Neptune's largest moon, Triton, was identified as one of the coldest places in the solar system, with surface temperatures plunging to extreme lows. Triton also exhibited unique features, such as nitrogen gas geysers and ice volcanoes that ejected debris up to 5 miles into its thin atmosphere. These extraordinary discoveries expanded our understanding of the diverse and complex celestial bodies that populate the farthest corners of our solar system. Recently, Voyager 1 made one of its most unsettling discoveries. Before delving into this alarming finding, let's reflect on the spacecraft's monumental achievements. The early observations of Jupiter and Saturn's moons left scientists in awe and challenged previous assumptions about these distant worlds. Moons once thought to be barren and inactive, like our own moon, were found to be rich in geological activity. Voyager 2, in particular, made history-making achievements during its journey. In 1986, it became the first spacecraft to fly by Uranus, and just 3 years later, it performed a flyby of Neptune, becoming the only spacecraft to do so. As the Voyager spacecraft continued their missions, NASA implemented various strategies to extend their operational lifespans. Over the past few decades, certain instruments and heaters have been deactivated to conserve power, ensuring that these resilient explorers can continue their work well into the next decade. The projected mission end date is set for 2030. For the scientists and engineers involved from the beginning, the Voyager missions are a source of immense pride and nostalgia. Their tireless efforts have far exceeded expectations, and the wealth of data provided by the spacecraft has led to countless scientific discoveries, inspiring future generations of explorers. Specialists and space lovers alike, Voyager 1 and Voyager 2 were not simply customary rockets. They were the result of careful planning, robust designs, and rotation speeds typically slower than the hour hand of a clock. This innovative setup minimized visible blurring, allowing the spacecraft to capture data and images simultaneously as they traveled through space. Even before their encounters with the outer planets, their exceptional imaging capabilities began to captivate specialists and the public. The spacecraft started transmitting pictures of Jupiter well before completing their primary missions. These early images, showcasing swirling clouds and the famous Great Red Spot, fascinated audiences at NASA's Jet Propulsion Laboratory. However, it was the discovery of active volcanoes on Jupiter's moon Io that truly stole the spotlight. Slightly larger than Earth's moon, Io turned out to be the most volcanically active object in our solar system. The spacecraft's instruments detected consistent signals from Io, which were confirmed by the vivid images they transmitted, revealing volcanic plumes and a surface scarred by eruptions. One of Io's most significant volcanoes, Pele, erupted with a force many times greater than Mount Everest, covering an area nearly the size of France. Eventually, the spacecraft's cameras shut down to conserve energy and memory before their journey into interstellar space. It's important to note that the images they captured did not include Mercury or Mars for multiple reasons. Nonetheless, alongside Pioneer 1 and Pioneer 2, NASA also launched other impressive spacecraft, including Pioneer 10, Pioneer 11, and New Horizons. On February 17, 1998, Voyager 1 surpassed Pioneer 10, becoming the most distant spacecraft. Voyager 1 continued its solo journey for another 14 years before entering interstellar space on August 25, 2012. Although this milestone was reached in 2012, NASA did not publicly announce it until 2013. The discovery of the S8 tension, emerging from gravitational lensing studies, suggested a lower-than-expected value of S8 based on data from the Cosmic Microwave Background, CMB. The study of this phenomenon has led scientists to consider various theories, ranging from data errors to significant revisions in our understanding of gravity. Advanced simulations like the Flamingo project play a crucial role in providing insights into the interactions between dark matter and gravity in shaping the structure of the universe. Despite the challenges posed by the S8 anomaly, most low redshift measurements and CMB data still align with the standard cosmological model. This has led to the intriguing possibility that the universe may have undergone vast changes, challenging our understanding of its structure. Overall, the S8 tension presents a significant challenge to our cosmological theories and may require updates to our existing models. Voyager 1 and Voyager 2 represent the pinnacle of human creativity. Launched with the vision of uncovering the mysteries of our solar system and beyond, these remarkable spacecraft continue to inspire researchers and astronomers decades after their initial missions began. Their scientific contributions not only reshaped our understanding of planetary bodies but also propelled space exploration to unprecedented levels. Throughout their missions, the data they transmitted provided invaluable insights that have guided subsequent space missions and technological advancements. One of the most extraordinary aspects of the Voyager missions was their longevity and durability. Designed to withstand the harsh environment of space, both Voyager 1 and Voyager 2 demonstrated remarkable resilience for many years. They endured extreme temperatures, intense radiation, and the vacuum of space. Their imaging technology in particular proved revolutionary, allowing scientists to capture detailed images of distant planets and moons. The spacecraft's ability to relay data from millions of kilometers away provided a deeper understanding of planetary geology, atmospheres, and magnetic fields. Voyager 1's incredible ability to detect cosmic radiation and its pioneering work in studying Earth's radiation belts marked a crucial moment in space exploration history. Before Voyager, scientists could only speculate about the composition and behavior of the space environment. With its sensitive instruments, Voyager 1 provided direct measurements, laying the foundation for future missions focused on space weather and cosmic radiation. The discovery of Earth's radiation belts, later named the Van Allen belts, became one of the most significant breakthroughs of the 20th century in space science. Both Voyager 1 and Voyager 2 demonstrated the effectiveness of NASA's innovative engineering and mission planning. These spacecraft were developed with the utmost precision to ensure that each component functioned in harmony, collecting data across vast distances. Their ability to execute course corrections, adjust to the gravitational influences of planets, and withstand the intense radiation environment of deep space made them adaptable tools capable of performing a wide range of scientific tasks. Their extensive mission profiles, spanning from studying planetary systems to exploring the outer reaches of the solar system, showed that no mission objective was too complex for these highly advanced spacecraft. While the missions primarily focused on planetary exploration, their discoveries extended to a wide range of scientific fields. The analysis of magnetic fields, the study of planetary atmospheres, and the observation of solar phenomena provided new perspectives on how our solar system operates. In particular, the study of planetary magnetospheres and the interaction of solar wind with planetary magnetic fields helped scientists understand the conditions that make Earth habitable. Voyager 1's measurements of charged particles in Jupiter's magnetosphere, for example, refined our understanding of how the giant gas planet's magnetic field interacts with its moons and surrounding space. In addition to their technical achievements, Voyager 1 and Voyager 2 significantly contributed to expanding our knowledge of extraterrestrial life. While alien civilizations remain speculative, the data returned by these spacecraft, including atmospheric analysis and surface composition studies, laid the groundwork for future missions searching for signs of life beyond Earth. The possibility of discovering life on other planets or moons became an increasingly central topic in space exploration. Both Voyager missions highlighted the importance of understanding the potential for life in extreme environments, such as the icy moon Europa or the methane-rich atmosphere of Titan. The curiosity and excitement that followed the transmission of the first images of distant moons, planets, and stars ignited a sense of wonder that transcended the scientific community. These spacecraft were not only technical marvels but also symbols of humanity's collective drive to explore the unknown. Their images inspired countless individuals to pursue careers in science and engineering, playing a crucial role in shaping public interest in space exploration. This shared sense of discovery fostered a global appreciation for space science and technology, with scientists, educators, and enthusiasts coming together to celebrate the achievements of these spacecraft. As Voyager 1 and Voyager 2 ventured farther into space, their missions evolved in response to the changing landscape of space exploration. The focus shifted from planetary exploration to studying the broader universe. As they moved into interstellar space, the spacecraft took on new roles, examining the cosmic radiation environment and studying the magnetic fields of the interstellar medium. This phase of the mission introduced new scientific challenges and opportunities, as both spacecraft encountered regions of space never before explored by humanity. The latest anomaly detected by Voyager 1 has sparked renewed urgency and interest in the scientific community. Some suggest that these unusual signals may be the result of unknown cosmic phenomena, possibly linked to previously unseen particles or forces. Others propose that the spacecraft's instruments may have encountered regions of space where the laws of physics behave differently, offering new opportunities for investigation. Exploring these unknown realms opens the door to potential discoveries that could revolutionize our understanding of the universe. While speculation continues regarding the true nature of these signals, the scientific consensus remains cautious. The data could reveal new insights into dark matter, dark energy, or unexplained cosmic forces that have yet to be fully understood. With the development of advanced technologies and new methods of data analysis, scientists continue to investigate these anomalies, hoping to unlock the secrets they hold. Whether these findings lead to groundbreaking discoveries or are eventually explained by more conventional causes, the study of these signals adds another layer of intrigue to the already rich legacy of the Voyager missions. Ultimately, the story of Voyager 1 and Voyager 2 is a testament to the enduring spirit of exploration and discovery. These spacecraft, which have traveled farther than any human-made object, continue to push the boundaries of our understanding of the universe. From their groundbreaking discoveries of planetary moons and magnetic fields to their ongoing mission into interstellar space, their contributions will be felt for generations to come. As we look toward the future of space exploration, the legacy of Voyager reminds us that the pursuit of knowledge knows no bounds.